Part 2 of this lecture deals with other measures of variability, including the variance and standard deviation, as well as some consideration for choosing the best measure of variability for any given variable. We begin with the variance, which is a measure of the average distance of each score from the mean. This is typically used with interval ratio variables. Unlike the interquartile range, the variance takes into account all the scores, not just two. Here's the formula for the variance for some variable y. Notice that if we look at only a portion of the formula, it looks like a kind of average. Well, that's because it is. The variance is the average deviation from the mean, expressed in a squared metric. And in the formula, s squared sub y denotes the variance of some variable y. In the numerator, we have the sum of the squared deviations from the mean, where the Greek letter sigma stands for the summation operation, telling us to take the sum of the quantities of y minus y bar. Y is just some variable, and y bar is the mean of the variable y. And then those quantities are squared before being added together. In the denominator, we have n, which is the total sample size, or the total number of cases, and we subtract 1. Now you might be wondering, why do we subtract 1? Well, it has something to do with something called degrees of freedom. So, what do we mean by degrees of freedom, or df? Degrees of freedom refers to the number of scores that are free to vary in calculating a statistic. In calculating the variance, our starting point is the number of cases, n. So this is what's free to vary. Now, we're assuming here that we're starting with sample data. And notice that in order to calculate the variance, we first have to calculate another statistic, the mean. In this case, rather than using the true mean, or the population mean, we're using a sample mean. And therefore, we're imposing one restriction on our data. And therefore, we lose 1 degree of freedom. Let's look at a very simple example of how to calculate the variance for a hypothetical sample of 5 cases, for which we have data on age. Let's suppose that their ages are 21, 31, 23, 41, and 20. We start first by finding the mean, and we do that by taking all 5 of the ages, adding them together, and dividing it by 5. The resulting value is the average age, which in this case is 27.2. The second step is to take the deviations from the mean, that is, take each of the categories, 21, 31, 23, 41, and 20, and subtract the mean from each one of them. Let's look at this step in a little bit more detail. So for the first person, who's age 21, we see that that person has a below average age. 21 minus the mean, 27.2, gives us a deviation from the mean of negative 6.2. The next person is age 31, and that person has an above average age. So 31 minus the mean, 27.2, gives us a deviation of 3.8 years. The third person is age 23, and when we subtract the mean age from that person's age, we get another negative deviation, a value of negative 4.2. Notice that we're going to take the deviations from the mean for all 5 of these values. When we do that, we find that they add up to 0. This is no coincidence. The mean has a very special property. When it's subtracted from every value in an array of numbers and added together, it always sums to 0. That's because the mean is the arithmetic center. It perfectly balances any value below the mean with those values above the mean. And so this is actually a problem. When we're trying to calculate the average deviation from the mean, and we always find that the numerator is going to sum to 0, we have to do something to exaggerate the difference between the mean and those values below it. So what we do is we basically square the deviations from the mean. Squaring gets rid of the negative numbers and makes sure that our sum of square deviations adds up to something other than 0. So that's the third step in calculating the variance, taking the square deviations from the mean. Let's look at this in more detail. So recall that the first person, who's age 21, had a below average age. That person's age was 6.2 years below the average age. When we take that deviation from the mean, negative 6.2, and square it, we get a positive value, 38.44. The next person, who's age 31, recall, had an above average age. That person was 3.8 years above the average age. When we take that deviation from the mean, 3.8, and square it, we get a positive value, 14.44. For the third person, that person also had a below average age, and the deviation from the mean for that person was negative 4.2 years. When we square negative 4.2, we get a positive value, 17.64. Basically, we're going to square the deviation from the mean for all 5 of these cases. The next step is to take the sum of the square deviation from the mean. So here, I've added the 38.44, 14.44, 17.64, 190.44, and 51.84, and got 312.8. The next step is to divide that by the number of cases minus 1 to get the average deviation from the mean. So if we take 312.8 and divide it by n, or 5, minus 1, which equals 4, we get 78.2, and that's the variance. How do we interpret the variance? Well, it turns out that it's quite difficult to interpret the variance because it's no longer in the original metric of the variable. Remember that we squared the deviations from the mean in order to get rid of the negative numbers, in order to make sure that the deviations from the mean didn't sum to 0. In so doing, we change the original metric of the data. But if we take the opposite operation of squaring, the square root, we can return the variable to its original metric. Taking the square root of the variance actually gives us another statistic, something called the standard deviation. The standard deviation is very much like the variance, but it's in the original metric of the variable. Here's the formula for the standard deviation. We denote the standard deviation as s sub y. It's equal to the square root of the variance as squared sub y. Or it can be calculated directly by taking the square root of the sum of the deviations from the mean of the variable squared divided by n minus 1. Let's calculate the variance for our hypothetical example of the 5 ages. Recall that the variance was 78.2. When we take the positive square root of that value, we get the standard deviation, which we find here is 8.84. So what does that mean? Well, we found that the average age for this group of 5 cases was about 27 years, and now we find that they have a standard deviation of about a little over 8 years. In general, interpreting the standard deviation and the variance can be a bit challenging. Both values range from 0 to infinity, and basically, the higher the value, the more variation around the mean, and the lower the value, the lower the variation around the mean. Standard deviation and variance tell us very little by themselves. They're more useful in comparisons across distributions. Let's consider again those 2 grade distributions that we saw earlier in the lecture, one from Professor Brown and the other from Professor Yamamoto. Remember that Professor Yamamoto's distribution was more widely distributed around the mean, and therefore it should have the higher standard deviation. So if we refer back to the figure, we can see that Professor Brown's distribution is more narrowly clustered around the value of the mean, and therefore Brown's distribution should have the lower variance and standard deviation. We can also calculate variance and standard deviation from a frequency distribution. This is a whole lot easier than calculating using raw numbers, especially if we're dealing with a large data set. But we have to change our formula a bit and just add one new step. So here's the formula for our variance if we start with data in the form of a frequency distribution. Notice that we have to add f, the frequency, to the formula. Now in the numerator we have the sum of the square deviations from the mean weighted by their frequency. And in the denominator we have the same n minus 1. Let's look at an example of how to calculate the variance using the variable number of children. Here are the steps involved. First, we have to calculate the mean. Second, we have to take the deviations from the mean. Third, we have to square the deviations from the mean. Fourth, we have to weight the frequency, the square deviations from the mean by the frequency. This is an extra step that we take when we're calculating the variance from a frequency distribution. Fifth, we have to take the sum, and then sixth, we have to divide by n minus 1. So, this table shows the calculations for the average of number of children. Recall that we found this value in an earlier lecture when we looked at measures of central tendency. We found that for the number of children in this sample, they have just under 2 children on average. Or more specifically, they have 1.89 children. So, Let's start by taking the values of the categories of number of children and listing their respective frequencies. The first step is to take the deviations from the mean. So for each of these categories, 0 through 8, we first take the mean 1.89 and subtract it from each category. Next, we're going to square the deviations from the mean. Again, this is to ensure that they don't add up to 0. And then the additional step, we're going to weight those square deviations from the mean by the frequency. Let's take a look at that in slightly more detail. We'll start with category 0. So here we see that there are 536 cases that have 0 children. If we find the deviation from the mean, we're going to take 0 and subtract the mean, 1.89, and we get a value of negative 1.89. If we take that value, negative 1.89, and square it, we get a value of 3.58. And then if we take the 536 cases and weight the square deviations from the mean, that is, multiply them by 3.85, we're going to get the weighted square deviations from the mean. The fourth step is basically to take the sum of the weighted square deviations from the mean across all the different categories of the variable. And then we're going to divide that value by n minus 1. Notice here that we have 1,971 cases. And so we're going to divide our weighted sum of square deviations from the mean, 5,523.98, by 1,971 minus 1. And that gives us a variance of 2.8. From the variance, we can calculate the standard deviation by taking the square root of the variance. And so our variance was equal to 2.80, and its square root equals 1.68. So our standard deviation here is 1.67. How do we interpret that? Well, we could say that the standard deviation is just under 2 children. Now we'll consider how to choose the appropriate measure of variability. And the choice depends basically on two things. First, the level of measurement, and second, the shape of the distribution. So for nominal and ordinal variables, we really only have one choice, the index of qualitative variation, or IQV. And this basically treats ordinal variables as if they're nominal variables. That is, we lose the information on rank ordering. For interval ratio variables, our choice is anything but the IQV. That is, we can choose the range, the interquartile range, the variance, or the standard deviation. But the best choice is the standard deviation. That's because it takes into account all the data and is in the original metric of the variable. However, the standard deviation is a bad choice if the distribution is skewed. In that case, the interquartile range, which you'll recall doesn't take into account the values at the tails of the distribution, is the better choice. As an example, let's look at the distribution of number of children to figure out what's the best choice for the measure of variability for this variable. Let's start by looking at its distribution. Here's a histogram showing the number of children. And here's what it would look like as a box plot. So notice that there's a very obvious positive skew here. While most of the distribution is in the left tail, we have some high value, in this case, some household with 8 children, pulling the distribution towards the right tail. So this is a skewed distribution. In that case, the average is in the middle of the distribution, and therefore the variance and standard deviations aren't a very good indicator of the variability around the center. Therefore, we should use the interquartile range as the measure of variability for this particular variable.